All right, hello, welcome to EEE 117. This is Dr. Trace Duesman here. We're going to talk about Chapter 13, Circuit Analysis in the Laplace domain. So if you remember last week, we talked about Laplace transforms and how to go from the time domain to the frequency domain as a prelude to doing circuit analysis, where now we're actually going to talk about it. So the first thing we talk about is what are the typical devices we see in circuit analysis and how do they translate to the frequency domain so you could do Laplace transforms and circuit analysis. So first thing will be your voltage sources. So you remember you always have a voltage source with a switch in series that will turn on and close in to power the circuit. You also have a current source where you have a parallel switch, and when the switch is in, the current will just loop around this circuit and nothing will go out. Sorry, the current will loop around the switch and nothing will go out to the main circuit. When you open up the switch, the current path will then divert to the main circuit. So this is how you turn on and off current sources and voltage sources. Okay. Typically, you have resistors in the circuit. So these dissipate power. You have capacitors that store energy. It'll try to oppose the change in voltage, but can have current spikes whenever you need to charge up the capacitor. Okay. Inductors store energy in the magnetic field. The inductor tries to fight current and opposes a change in current. And whenever you do try to force the inductor to change current, you might have a large voltage spike across the inductor because it's trying to refuse to change the current. It turns into a voltage source temporarily. Okay. So far for circuits, these are the three, or the sources, and then three passive devices you typically see, right? So first thing we're going to talk about is doing the conversion. So we have a DC voltage source of 100 volts with a switch. This converts to 100 divided by S, where the divide by S is a step function to represent the switch. So you literally just take the voltage, swap it over, divide by S, and this is your Laplace domain voltage source. Current source, very similar. You take the switch out and just put divide by S to represent the switch turning on. So you have a current with 100 divided by S as a current source for the Laplace domain. Lastly, we have AC volt, any type of alternating current voltage source or current source to be exact. You have V of t is equal to 200 cosine of 377t, right? Remember 377 is your omega, which is the radians per second, or indirectly the frequency of the circuit. You could convert that over to the Laplace domain. Look at your table. It's going to be 200, which is a voltage magnitude, times S divided by S squared plus omega squared, which is 377 in this case. Okay. So these are the three types of sources you'll typically see. Okay. Now, let's talk about a resistor first. So we know we have voltage across resistors. The current will be induced because of voltage, and the ratio is V equals I times R. This is a standard Ohm's law, right? Because it's only multiplication, it's a direct conversion to the Laplace domain. There's no extra steps. You literally, any V of t turns into Vs to represent that we're in the Laplace domain. Any current I of t is replaced by capital I of S to signify current is in the Laplace domain now. And then the resistor carries over because it's just a number, right? So you could quote unquote redraw the resistor. It's going to be the same with capital V and capital I going through. Okay, so resistor is obviously easy one. Nothing really changes. Okay. So if we do resistor, let's do a small circuit analysis with resistors here. So you got three resistors, R2 and R3 in series, and that combination is in parallel with R1. So you could rewrite this as R1 parallel, open parentheses, R2 plus R3. R1 is 10, R2 and R3 are both 5 each, and the voltage source is 100 divided by S. So this is already in the Laplace domain circuit. Let's just do a basic circuit analysis. Now, the beauty about this is once you're in the Laplace domain, you could use any basic circuit theory you've used before. So here, obviously, we could crunch these resistors together. So R2 and R3 is 5 plus 5. You double bar parallel to 10. And then this will be really 10 parallel to 10. And you know the trick is going to be the two resistors multiplied on the top divided by them added together. So you're going 10 times 10 divided by 10 plus 10 is 5. So our net impedance is 5 ohms of the circuit after we combine all the resistors. To find a current, that's just going to be Ohm's law now. I is V over Z, where you have 100 divided by S, and 100S comes from the voltage source right here, right? And then you're also going to multiply by, or you're going to divide by 5 as well. So the 5 is on the bottom right here. So chunk this out, it's just going to be 20 over S, which makes sense. If it's 100 volts, you have a resistor of 5, you should expect 20 amps flowing through. And the divide by S is to represent the step function because we're going to turn the circuit on at t equals 0. Okay. So nothing really changes. I guess the big difference is you got to just remember to carry the S over because of the switch. Now it's going to get a little more complicated. Let's talk about inductors, right? Inductors, they don't really play that nice in terms of current. So we have inductor, we have current flowing through, a voltage will result as we flow, the current flows through an inductor. Okay, you could figure out this voltage because it's going to be equal to L times di over dt. Remember what di over dt means is the rate of change. If we try to change a current really fast across the inductor is going to fight us. And so if we try to push a lot of current flowing through here to the positive terminal, and the inductor won't let anything go, we're going to have a lot of charge built up on the A terminal and nothing on the B terminal. So you're going to have a big voltage across it. So the faster you try to change a circuit, change the current in the circuit, the more voltage difference will be across the inductor because the inductor it's like a traffic jam. It's going to stop the cars from flowing. So on one side, on A, you're going to have a giant traffic jam. On B, it's going to be clear roads. The interstate will be clear because there's no cars because nothing's going through. So what's your voltage across there? It's going to be a lot because you have a lot of charge on A and nothing on B. So your voltage will spike up. Okay, so that's why we say voltage can be very spiky on an inductor. But it really depends on how fast you change the current. If you change it instantaneously, it's going to have near instantaneous. It's going to have an infinite voltage spike. Okay, so V equals L times di over dt is your voltage. Your current, on the other hand, if we force voltage across an inductor, it's going to keep building the magnetic field. So I is going to be equal to 1 over L times the integral. Integral is just adding up the voltage from 0 to t. So this basically says count how many seconds of voltage is on, divide that by L, and that's the current. So if we keep the voltage on for 10 minutes, we're going to have like 50,000 amps. If we keep the voltage on for 1 millisecond, we're going to get almost no current. So that's why it's integral. Is the more voltage we apply to it, the more we build up the magnetic field, the more the current flows. Okay. So this is all time domain stuff. Let's convert this to the Laplace domain. So if you remember, d over dt is multiplied by s, integral is divided by s. So we can now say V is equal, so voltage is equal to Z times I, right? Or sorry, the voltage here, V of t is equal to V of s, so that's a conversion over. L comes with us. D over dt up here comes to s down here. And then I just comes here with us, so it's capital I of s, okay? So this is the new V equals S times L times I. Now we could convert I over to where I is equal to V over Z, where I is equal to V over S times L. And we could see the new impedance of the circuit is S times L. Okay. So the nice thing about this is now we could use this inductor like a resistor in the sense that we have a hard impedance of S times L. Up here, there was no easy way to pull out an impedance. It was jumbled up in calculus, which it's very hard to pull out something. You can't say L times d over dt is Z. That doesn't make any sense. The d over dt needs to have a target. But down here, we could take Z and isolate it and just say this inductor has an impedance of S times L, not Z, sorry. So now I could see a voltage across inductor, current flowing through it, and impedance is S times L. I can now use Ohm's law to figure out anything I want here, which is way better than differential equations, right? That's the whole reason why we're doing this. Okay, so big thing here is the inductor is S times L. Now, let's see it in action. So we have a simple RL circuit, R is 10 ohms, L is 1 Henry. voltage is still 100 over S. Let's figure out the current flowing through. Okay. Now the Z is, because these are in series and S of L is now an impedance, it's technically in ohms now. You could say the impedance of these two branches adding up is R plus S times L. Where now we have an impedance, I know my voltage, I could then use Ohm's law, V equals I times Z, to figure out my current. So current I would be equal to voltage, 100 divide by S, so that's our main voltage, and we're going to divide by Z. So we're going to open bracket, multiply by 1 over SL plus R, where this is Z in the bottom right here. Okay, so this is V divided by Z is equal to I, which is Ohm's law. Okay. Now, we could kind of make this more simple by plugging in L. L is 1, R is 10, and then we have over here I of S equals 100 divided by S, open parentheses, 1 divided by S plus 10. This is our function for the current. Now remember, S is the only variable here. If we know our frequency, we could plug in frequency in terms of S and then get a hard number. So if I have 1,000 hertz, we could do 2 pi 1,000 to get radians per second and plug in that number for both of these S's, and then we'll get like, I don't know, 37 amps. Okay. And obviously, as the frequency changes, this number will get smaller. The bigger the frequency, the smaller this current's going to get. Right. Which makes sense because we talked about in the phasors, the higher the frequency, the bigger the impedance of an inductor. So you expect the current to get smaller. Okay. But the big trick here is there's no differential equations needed. It's just arithmetic. Okay. And that's the beauty of using the Laplace domain. So we can do the same thing for capacitors. Capacitors are quote opposite of inductors. Where you have a capacitor here, you got voltage across it, you got current flowing through. So current through the capacitor is always I is equal to C times dV over dt. Okay. Now let's step back real quick. Physically, what does this mean? If I put if we have a preset voltage on the capacitor and I try to add more, I want to force more voltage in. So let's say this voltage is 5 volts, I want to make it 10 volts, right? The capacitor has a lot of room for electrons. So to raise the capacitor to 10 volts, we're going to dump a lot of current to fill up all the room, all the plate with electrons. So that big old cookie sheet, we're going to have to dump thousands and thousands or millions and millions and millions of electrons to fill up that cookie sheet. So if I try to change the voltage from 5 to 10 instantly, that d over dt is really big. Sorry, if I try to change the voltage from 5 to 10, I'm going to get a huge current spike to fill up the cookie sheet to bring the cookie sheet from 5 volts to 10 volts. Okay, that's the reason why we have a giant current spike, is we need to flood in the electrons on the capacitor to raise that voltage up. Okay. So that's why if the faster I try to change this voltage, the bigger my d over dt spike is, the bigger my current spike will be. Now, obviously, the bigger the C, the bigger the current, because a big C means a giant sheet of a big capacitor. A small C means a small capacitor. So the bigger my capacitor, the more electrons I need, the more current that needs to flow to fill up the capacitor to bring the voltage up. Okay, so that's what d over dt means. It means the faster you try to change the voltage, the bigger the spike of the current. Okay, opposite to that, if I have voltage here, and let's say I have a capacitor and I'm constantly putting 10 amps over and over and over again, right? What's going to happen to the capacitor? It'll slowly build up voltage, right? Because remember, capacitor is an energy tank. So the more current I push in, the more electrons I put into the capacitor, the bigger the capacitor gets, the higher that voltage gets. And this can keep on building forever until I stop putting current. We can represent that by taking the integral of the current. So the longer the current stays on, the higher the voltage. If I put the current on for 1 millisecond, I'm going to get a very small voltage. If I put the current on for 24 hours, I'm going to get a huge voltage, right? Now, you're going to divide by C because the C is how big the capacitor is. The bigger the capacitor, the more current is going to be needed to raise the voltage. Okay, so that's why you have this integral here. It's just counting how much current and how much charge you're dumping into the capacitor. Okay. I always like to say this over and over again because I believe if you truly understand what's the physics behind the capacitor, the all this math is like simple. It makes sense rather than just memorizing d over dt and integrals. Okay. So even if so, we have these two. I mean, it's calculus, it's integrals. Those are hard, right? Especially when we try to do some circuit analysis. Let's get away from this. We know we could do Laplace transforms on this equation and have I of t convert to I of s. That's a direct conversion because it's a variable. C comes with us. D over dt is an s. And then a v over t times and turns into capital V of s. So we almost have Ohm's law right here, kind of, where we have a c times s is the extra part. So if I swap the c of s on the other side, I'm going to get v equals z times I, where z is actually 1 over s times c. So what this tells me is now I could represent this capacitor as an impedance where z is equal to 1 over sc. As long as I could crunch this number, I could now treat this resistor like I can now treat this capacitor like a resistor because it's an ohms. So I can add them, divide them, do all your circuit analysis, and pretend that this is a resistor, except impedance is 1 over S times C. Okay. And that's the beauty is we're basically trying our hardest to get away from differential equations because differential equations suck. Okay. Arithmetic easy, differential equation hard. So let's do another example. We have an R, we have a capacitor, a resistor and a capacitor, they're in series. So our impedance Z we could just add them together. It's literally R plus 1 over SC. If I want to find a current flowing through it, I could again use Ohm's law. V equals I times Z. I have Z already. I have V. It's 100 over S. Okay. Now, swapping Z to the other side, it's going to be I is going to be equal to V divided by Z. So V is 100 over S. We have that up here. That's the voltage source. We're going to divide by Z. Z is R plus 1 over SC. So we're going to multiply by 1 divided by R plus 1 over SC. Okay, so this is our divide by Z right here. Now we just got to do arithmetic. So in general, the S variable, you want to get away from any denominators like this. Just divide by SC is a little complicated. So we could literally take this S and multiply it into the bracket. So we're going to take this S, multiply by R, so we're going to get an SR. We're going to take this S and multiply into 1 over SC. So you can have S divided by SC. The S is canceled. You're just going to get 1 over C right here. Okay. Now we're going to just plug in some numbers. We're going to have I of S equal 100, open bracket 1 over 10 times S plus 2. And then we like to keep the S variable by itself. Typically the highest polynomial, you just want that. You don't want a coefficient in front if you can help it. So the easiest way is let's just pull a 10 out to the front. So if I take a 2, I could say this is 2 is actually 10 times 0.2. Remember that trick from middle school, right? Take a 2 and just open it up as 10 times 0.2. Okay. So 10 is on both the denominators, you could pull it out to the front. And then 100 divided by 10 is 10. So from here to here, we have 10, open parentheses, 1 divided by S plus 0.2. Okay. So it's a little arithmetic trick. So at the end of the day, this is a function of our current, which is a lot easier than the differential equation equivalent, right? Again, if we know a frequency, we could just plug in frequency of S and get a hard number like, I don't know, 15 amps. Okay. So remember, the whole point of this circuit analysis is finding a circuit, finding the current in terms of circuit parameters and frequency. Because when the time comes to use this, we're going to plug in a certain frequency for the voltage, right? It could be 100 hertz, 200 hertz, 300 hertz. We might have a little function generator with a knob where we're going to turn from 100, 200, 300, 400, 500, 600. And what we want to see is we want to see the current change as the frequency changes. Because a lot of times when we're using cell phones and communication equipment where we'll be hot swapping frequencies all over the place, I need to know how a circuit operates when frequency changes. And that's why you have this function. Okay, this function I is never going to change unless we rearrange the circuit parameters. So this circuit, this current is locked into this circuit configuration, so you don't have to do this analysis every single time. Okay, build this into a spreadsheet and then just change the frequency in one of the cells, and you can just see the number pop up over and over and over again. Okay, that's the whole point of circuit analysis, right? We want to get a circuit to where we could predict what's going to happen when we use it for the next step. Okay, so those are the four main, the resistor, inductor, capacitor, and voltage sources. That's how we bridge everything together. We can pretty much start doing circuit analysis now, right? Any type of circuit analysis you used in engineering 17 is valid as if they were in the time domain. For example, Ohm's law, node analysis, mesh loop analysis, superposition, Norton-Thevenin's theorem, source transformations. There's a few others I didn't mention, but I mean, any engineering 17 circuit analysis for DC is valid for this as well. Okay. The big difference is you need to do the extra work to make sure the circuit is transformed into Laplace domain. You can't do half and half. You can't transform half the circuit and then leave the other half intact. It needs to be all or none. Okay. So let's do an example of all three inductors, capacitors, and resistors put together. So we have this circuit. It's a voltage, right? You have a switch that opens up. Okay, so it's a little bit different. Notice that this circuit is on all the time, and then we open up the switch. Okay. So how can we figure out this voltage? How can we figure out the current flowing through the circuit or the voltage across here? Okay. So V out can be figured out. So V out is the voltage across a resistor. This could be figured out in terms of the whole circuit. Well, if you remember your voltage division, you have a main voltage across all three of these components, right? Because it's in the loop. If I just want the voltage across the resistor, it'll be the input voltage, Vn, times the resistor I'm on, divided by all the impedance of the loop, which is R plus SL plus 1 over SC. Okay? So this is just basic voltage division and treating the inductor and capacitor as impedances. Okay? Let's clean this up a little bit. Remember this, we don't like this 1 divided by SC, so the first thing we do is we'll multiply the whole equation with an S times S. So S on the top and S on the bottom. This will get rid of this S on the bottom here. So multiply S on the top. First off, we could take out Vn. So Vn comes out the bracket. We're going to have R times the S. So we have SR. We're going to divide by S goes into everything in the denominator. R times S comes here. We're going to have S squared times L right there. And the S divided by S cancels. So we're going to have a 1 over C here. Okay. Next thing to remember is the highest polynomial. You want to have it by itself. We won't get rid of this L. So we're going to multiply by 1 divided by L on both the top and the bottom. Okay, so S times R divided by L becomes R over LS, right? S squared L divided by L cancels, so you have an S squared that comes to the front here. S times R divided by L equals S times R divided by L, which is right here in the middle. And then 1 over C times 1 over L becomes 1 over LC. Okay, this is the proper form because this is now in a quadratic form. Because if you remember from last week, if we ever need to go and do the inverse Laplace transform, we need to make sure we have a quadratic form on the bottom so we can find our roots. So it's very common that your output will be in this quadratic form. Okay, so this is how you represent your voltage right here. Okay. Now, what we can do is we can now plug in our resistors, capacitors, and inductors, R, L, and C, into the previous equation to get actual numbers, not just variables everywhere. Okay, so R is 10, so you put a 10 and 10 here. L is 5, so you put a 5, 5, and 5 there, there, and there. And we just plug and chug, right? C comes right here. You have 100 over S is right here. And so we just number crunch this between 100 times S over S squared plus 2S plus 1. Okay. Now, this is a quadratic form. We could find roots pretty easily. It's going to be 100 times 2 divided by S plus 1, S plus 1, right? I actually made a mistake real quick. I didn't carry this S over, did I? Oh, no, no. The S got canceled here and here, right? This got canceled, that got canceled. Okay. Sorry, I'm going to confuse myself. Yeah, so this obviously looks a lot nicer, right? And again, this now we can now have a formula to figure out the voltage across a resistor for the whole circuit. And as the frequency changes in the source, we could just plug in a frequency of S and get an easy number. Again, this is where you would just program it in Microsoft Excel and just do iterative approach to do frequency from like 100 to 10,000, 100 intervals, right? I mean, if you know how to program in Excel, you could do that easily. Okay. So let's go ahead and do the same thing here. A circuit here where we're going to go and try to find the output voltage on the resistor, which is divided across the inductor, capacitor, and resistor, just like the previous exercise, right? So find your equation for your voltage across the resistor with regards to the inductor, capacitor, resistors, and the input voltage, right? Don't forget you need these to be a Laplace domain. So go ahead and do your transformation, right? Next, for the exercise is we're going to give you variables R, C, and L. So go ahead and figure out, plug them into your output voltage and try to find your quadratic formulas and get your roots, right? That's what poles and zeros are the roots of your output voltage, okay? So go ahead and try that. We'll come back in 15, 20 minutes to see how you did, and we'll check your work. So we'll see you guys in a few. All right, welcome back to EEE 117 after exercise. So let's go ahead and see how to solve the Sears RLC circuit. So first thing we got to do is we got to remember, we treat all your inductors and capacitors like resistors, except your inductor impedance is SL and your capacitor impedance is 1 over SC. So using voltage division between the resistor and everything else, you have your input voltage Vn times R as a resistor across, divided by the impedance of all three of them in series, just R plus SL plus 1 over SC. Multiply both top and bottom by S to get rid of this division, divide by S over here. So you can get Vn, which is taken out of the brackets, S times R on the top. This R has another S multiplied into it. So you have SL down here. We're going to have an S times an S to an S squared L, 1 over SC times the S is canceled. So we're going to have 1 over C, right? Then we want to get the highest polynomial by itself. So we got to get rid of this L. So we're going to multiply the top and the bottom by 1 over L to cancel out. So we're going to have SR divided by L right here, R L over S. Then we're going to have SR divided by L, which will then go put in the middle, R over L times S squared, L divided by L, the L's cancel, we get S squared in the front. And we have a 1 over C times 1 over L, which is 1 over LC. Okay, so this is our quadratic form where we want to find our output voltage. Now we're going to start plugging in numbers. So our output voltage is 20 volts. So we're going to have 20 over S times, and then we're going to plug in R, C, and L here. So we're going to have 3 over 0.2 and so on and so on. So just number crunch this all. We're going to have 20 times 15 divided by S squared plus 15S plus 15. Using quadratic form, we could split this up where we're going to have S plus 5 times S plus 10. So this is your end result for this new circuit. Now notice, because we have different RLs and Cs, our values are vastly different than the previous example. And that's the whole point of this, right? But again, now this particular circuit is now dialed into this equation. So if you ever need to find your output voltage, it's just a matter of changing the frequencies and plugging, chugging right and doing this analysis over and over and over again. Okay. So that's pretty much how you do that. Let's keep on moving. So here we're going to talk about, show you some more examples of how to use your Engineering 17 analysis. So let's look at node analysis. So here, before we do anything, right, we have this problem, and this is a very hard problem in time domain. it's a node in the middle with two inductors and two resistors, and you have a voltage, DC voltage of 366 volts that's getting turned on at t equals 0. Okay. First step before we do anything else is all this needs to get converted into the Laplace domain. Okay, so this 366 with this switch, that gets converted to just a voltage source with no switch, because the switch is represented by a divide by S right here. So there's 336 divided by S. Okay. Inductor 8.4 Henry turns into 8.4 S. Inductor 10 Henry turns into 10 S, and the two resistors follow with us. Okay, so now this is the circuit is in the Laplace domain. We could treat all your inductors as additional resistors. Now we can start doing node analysis. So remember the whole idea of node analysis, you choose a node. We're going to choose VA right here. And then all the current has to equal to 0. Or another way I like to think about it is current flowing in from the source. So we have I1 flowing in. It's going to be equal to the current flowing out down bottom, which is I3, and the current flowing to the right, which is I2, right? So whatever current flows into VA must also flow out. So in this case, I1 is equal to I2 plus I3. Now we could figure all this out. Current I1 is the voltage across the inductor, which is the voltage source minus VA. So you have 336 divided by S minus VA, and then you divide by 8.4 S, right? So that's your current flowing in. Your current flowing I2 from VA through the 10S inductor through the 48 resistor can be figured out as the voltage difference, where we put a ground down here, so the whole bottom part is a ground. So the voltage across these two inductors and resistors is VA minus 0 right here. So you have VA minus 0, then put a minus 0, divide by 10S plus 48 right here. Lastly, the current I3 flowing down is VA minus 0 over 42 ohms. So VA divided by 42. Okay, so this is your KCL equation. Okay. Now we could do our math. Okay, so we could take VA and pull it out from the top. So we have 3 and put 336 on the other side. So we have 336 divided by 8.4 S squared is equal to VA open bracket 1 divided by 8.4 S plus 1 divided by 10 S plus 48 plus 1 divided by 48. Okay, do some number crunching through here, and then we also know I1 is equal to 336 over S minus VA over 8.4 S. This I1, remember, is just this right here. Okay. We know I2. I2 is this one over here. That's just VA over 10S plus divided by plus 48. So VA divided by 10S plus 48 is I2. So notice we have 3 equations and 3 unknowns. VA is one variable, I1 is another variable, I2 is another variable. So there's 3 variables, 3 equations. We can't solve this, leaving S as a variable. I'll leave that up to you. Use your computational methods. Wolfram alpha, because this is probably not something you can easily do on paper. Quickly, at least. So a lot of algebra. And then you have I2 is equal to 168 divided by S cubed plus 14 S squared plus 24S. That's I2. And I1 is 40S plus 36 divided by S cubed plus 14S squared plus 24S. Okay. And so now, again, if you ever want to know your actual current, just plug in frequency of S and you're done. Now, I know it looks like it's a big step here, but I guarantee you, if you try to do this with differential equations, you're going to have 3 simultaneous differential equations to solve. And we've never learned, so far in college, you probably never learned how to do simultaneous differential equations because it's way too hard. Okay. This is still easier than simultaneous differential equations. I don't even know how to do that. Okay. So that's just the power of using Laplace domains. Is I'd rather just number crunch algebra, because this, between here and here, you could just load up Wolfram alpha and just say, hey, these are my 3 linear equations. Just go ahead and solve this. Just hit enter button and go. Okay. Wolfram alpha might have some issues trying to give it simultaneous differential equations. You might, but it would probably be a lot more complex to figure out the syntax and plug it in. Okay. Plus, you got to remember, back in the day, people didn't have Wolfram alpha to do all this. They had to do all this by hand. Okay. So that's node analysis. We could do mesh analysis as well, where we do loop equations. So we have the same circuit all over again. So we have the same Laplace domain circuit. Let's draw our two loops. We have I1 and I2. Okay. So remember how loop equations works. We have I1 going clockwise. It's going to enter in the voltage source. So this is going to be negative 336 over S. And then we're going to add the voltage drop across 8.4 S. So the voltage drop is always 8.4 S times I1. And then we're going to add the voltage drop across the 42 resistors, which is 42 times. Now we got to be careful. I1 is flowing from the top into the resistor, so that's a positive I1. But current I2 is flowing from the bottom, so they're opposing each other. So I2 must be negative, so it's minus I2. And all this needs to equal 0 because KVL means the voltage across one loop must all equal 0 at the end of the day. Okay. Now for I2, we could do the same thing. I2 is flowing clockwise. We're going to go through the 10S resistor. So the voltage across 10S is 10S times I2. The voltage across 42 is I2 times 48. I'm sorry, 48, not 42. Okay. And now the voltage across the 42 resistor is the I2 flowing in, which is positive, but I2 is flowing against it, which is negative. So it's going to be I2 minus I1. And now all has to equal 0 because I remember again, KVL says the voltage across one loop must equal 0 at all times. So we have two equations with two unknowns, I1 and I2. We can solve this to I2 if you just crunch it together. It's going to be 336 times basically all this. I'm not going to say it. You guys can see it. Okay. So this is I2 and I1 from these two equations once you crunch them together. And this, we could just do some algebra to rearrange it to where, get rid of some parentheses. We're going to get 168 divided by S cubed plus 14S squared plus 24S. I1 is going to be 40S plus 360 divided by S cubed plus 14S squared plus 24S. Notice that this is the exact same answer from node analysis, which I hope it is. It's the same circuit. We're just using mesh loop or node analysis. No matter which one you use, you should have the same, it should be the same answer at the end of the day. Okay, so this is again just another way to show you how to use mesh analysis through Laplace domain. And again, trying to use mesh analysis with differential equations is a nightmare. This is still easier. I rather do algebra all day than any amount of differential equations. Okay. So summary circuit analysis in Laplace domain, basically voltage and current sources are represented as the same type of source, taking into account a switch if present with that divided by S. Resistors are a direct copy over. Inductors can be represented as impedances, where the inductor impedance is S times L. Capacitors impedances. Capacitor can be represented as simple impedances, where Z of capacitor is equal to 1 over SC. Once you have all three of these in impedances, you can just then do your common circuit analysis technique, basically node analysis, mesh analysis, Thevenin norm, superposition, all that other stuff. Okay. So that's pretty much all I have for today, just to show you an introduction to Laplace transform, how do we use Laplace transforms to go into circuit analysis, and now how we do circuit analysis, okay? So thank you for showing up. We'll catch you on the next class period this week, and we'll probably do some more of this stuff and just get you used to it, okay? So thank you for showing up. You guys have a good day. See you later.